Hello everyone, my name is Xiaoli Su, and I'm from 3G Deep Lab. I'm very pleased to share with you our research on experimental and simulation study on microwave treatment for enhanced conic peak indentation of granites. Firstly, I will introduce why we use microwave to assist rock breaking and what experiments we carried out, and how we employed numerical simulation to support our finding. Let me begin with some background. Cutting hard rock is very challenging because it requires a lot of energy and costs significantly wear of cutting tools. Over the years, many methods have been explored to improve efficiency and reduce tool wear. Among these, microwave treatment has emerged as a promising approach. According to some researchers, microwave treatment can lower cutting force during rock excavation. Meanwhile, Lee also finds that a microwave can reduce the rock brightness potential, leading to less energy consumption. However, there is still a long road to industrial scale application. Our study aims to contribute to this progress by combining experiment results with numerical simulation. Now, let's talk about the fundamental mechanism of microwave-induced rock damage. First, we conduct lab tests using a microwave oven to heat the rock. Through this test, we discovered that certain minerals in the rock melt after 400 seconds heating. When this mineral melts, as reviewed by same image, they create small holes and micro cracks inside the rock. The internal damage significantly weakens the rock. In order to better explain our experimental finding, we also performed mineral-based simulations. These simulations indicate that minerals such as quantities, feldspar, and biotite expand at different rates when hit by microwaves. This uneven thermal explanation produces tensile stress at the boundary, which further promotes the formation of macro cracks. At the same time, the selective effect of microwaves also causes some internal region to heat beyond 800 degrees into melting and the phase change of the biotite. Next, we studied how microwave-induced damage affects the rock mechanic property after 120 seconds of microwave heating. The compressive stress dropped significantly, which suggests that heat creates internal macro cracks. We also find that treated samples become less brittle. They break more gently. Moreover, using a crack lineation-based brightness index, our results show that this property decreases non-linearly over time, reflecting that time-based weakening of the granite. Next, we conducted indentation tests of microwave treatment on rock failure behavior. These tests were performed on an instrument machine and employed a conic peak. We compared on-treatment sample with the treatment sample. Without microwave heating, the rock mainly shows tensile splitting, but after microwave heating, the rock fractures along the microwave-induced cracks. In untreated samples, the load displacement curves often show three distinct peaks, indicating multiple stages of fracture. However, after microwave treatments, the curves generally show one main peak. Additionally, the AE dates records fewer and weaker AE hits in the microwave heated sample, suggests that the microwave becomes less brittle. Microscopy observation also supports this finding. After 100 seconds of microwave heating, there is a noticeable reduction of surface debris. By 180 seconds, microcracks become widespread, and at 300 seconds, the rock internal structures appear significantly altered, indicate deep thermal damage. To understand how microwave affects the rock and how microwave behave under load, we built a numerical model. We began by assigning manual variability with a Weibull distribution. Then we applied microwave heating, which adjusted the rock material property based on temporary damage. After that, we conduct a compression to see how the rock fares under stress. We use a damage criterion to track the formation of the crack and the reduction of the rock stiffness. Next, we checked our model accuracy by comparing the result with the estimate date. After microwave heating, the simulations show that weaker region in the center of the specimens, matching the cracks and lower stress we observed in the lab. Under the loading, the model predicts shift from shear damage to the mix of shear and tensile damage, which is consistent with our estimate results. This similarity confirms that our modeling approach is reliable. Then, we begin by simulating microwave damage on a cubic rock specimen. The temperature evolution image shows a century hotspot that can reach to 500 degrees, creating a strong thermal gradient within the rock. Due to these gradients, tensile damage appeared on the outer surface, and the uneven heating leading to the damage zone appeared through the specimen. As the tensile damage develops, it reduces the Young's module of the rock, indicating a steady weakening of the material. Next, we use the microwave damage rock mode process with a conic peak. We compare specimens at different microwave heating times. At 0 seconds, we mainly observe that compressive damage near the peak tip with a small surrounding areas of tensile damage. But after 108 seconds, the tensile damage merges with the thermal damage, further weakening the rock. Finally, at 300 seconds, the tensile damage reaching its max extent leads to a noticeable reduction in compressive damage. On this side, we focus on the energy aspect of microwave-assisted rock breaking. From this graph, we see that as the microwave treatment increases, both the cutting work and the specific energy decreases, indicating that rock becomes easier to break. Meanwhile, the AE date also goes down, suggests that improved cutability. Overall, this finding shows that microwave heat times can significantly enhance cutting efficiency. In our study, we found 120 seconds of microwave heating have a good balance between damage and energy consumption. Before concluding, I would like to sincerely thank Professor Ranjith for his valuable guidance and support throughout my research. I also want to thank everyone at the 3G Deep Lab for creating a friendly environment. Over the past year, I have learned so much, not just about experimental and simulations, but also about teamwork. Finally, I would like to thank each of you for your time and attention. If you have any questions or would like to discuss further, I'm more than happy to continue this conversation.